All right. Hi, everyone. Welcome to the last seminar from our seminar series on optimization, algebra, and geometry. Today, we are pleased to have Professor Thorsten Theobald from the University of Goethe. Thorsten is going to talk about sublinear circuits and constrained signomial optimization. Thank you.
Okay, so thank you, Ali, for the introduction and for the invitation. Yes, I would like to talk about sublinear circuits, and the main part of the material is based on joint work with Riley Murray and Helen Naumann. And okay, now it doesn't click for whatever reason. Okay, now it does. Yeah, so the main model in this talk are signomials. I think many of you like polynomials, and signomials are a variation of polynomials, in some sense, a generalization. And in for polynomials, we usually think about linear combinations of terms, and here we are thinking about a linear combination of exponential terms. So I usually fix a ground support T. You can think of integer, non-negative integer vectors in the case of, say, polynomials. And here we are looking then at a linear combination of the exponential function of the scalar product of alpha times x. And the scalar product is the usual scalar product. And as I mentioned, when you're thinking about non-negative integer exponent vectors in T, then we are very close to the polynomial situation, because you can just do a variable transformation. Xi is equal to the logarithm of yi. And then this signomial, this exponential sum, becomes a polynomial in the variables y. And just there's a slight difference that because of this variable transformation, this is just a polynomial function on the positive orthant. But we are very close to polynomials, actually. And you should always have this in mind. And if you prefer polynomial, you can think about polynomials. So this would be a usual example. So if we have something like an exponential term of 2x1 plus 3x2, then in this polynomial world, this would be the corresponding term 5y1 squared, y2 to the cube. Then also, if we have the same situation that we have non-negative integer vectors, we of course have the correspondence that we have such a signomial to be non-negative on r to the n if and only if this associated polynomial is non-negative on the positive orthant, or equivalently if it is non-negative on the non-negative orthant. So we have a slight variation, and I would like to discuss optimization of these signomials. So I would like to determine the minimum of, say, a signomial f, where I have a certain constraint set S. And of course, it's possible that we're in the unconstrained situation that S is equal to the whole space. Okay, then we have the usual general strategy that I think is familiar to at least some of you, that we can reduce an optimization problem to non-negativity and to non-negativity certificates. Namely, when you want to optimize, to minimize a certain function f over a set S, we can look for the largest lower bound. That is, we look for the maximal gamma, so that f minus gamma is non-negative on S, and therefore we have reduced the optimization problem to a non-negativity problem. And therefore, we are very interested in so-called non-negativity certificates, say for classes of signomials for which one can easily certify the non-negativity. In the polynomial world, many things are meanwhile standard in the setting, meanwhile well known. There's the standard technique of sums of squares. This is very closely related to semi-definite programming, and then in the constraint world, this goes under the term of Laser relaxation. And this is the standard strategy in the polynomial world to work with, say, relaxations to tackle polynomial optimization problems. The signomial world, if you do not only work with non-negative integer exponents, is a little bit more general. In particular, also exponents like 1/2 are allowed. This corresponds to square roots, and therefore, of course, there are some additional applications. For instance, chemical reaction networks, aircraft design optimization, or other applications. So from that point of view, it's slightly more general. and we always, of course, have in mind also to tackle the polynomial situation. Okay, now the question is, what can we do there? So actually, in particular, if we have integer exponents, then we are basically in the polynomial world. Other than that, there are just very, very few techniques. And now, say the main techniques is based on the arithmetic geometric mean inequality, and the basic idea goes back to Resnick. And as before, I work with a ground support set T. And for notation, it's often convenient to denote subsets of T by A for terms with the positive coefficients, and with a B or with beta for terms with negative, or say with the possibly negative coefficients. And now the say first really interesting example is, say, a signomial, which has all the coefficients non-negative. So all the C alpha are non-negative. And we just have, say, one negative or possibly negative term. And I would like to explain you the combination to the arithmetic geometric mean inequality. And this can be seen if we look at a very special case. If we look at a very special case where all the coefficients C alpha sum to 1, where the C alpha describe a convex combination of beta. We describe beta in terms of the convex combination of these elements in alpha. And if d is equal to -1, then in this situation, f is always non-negative on the full space. And in order to see this, we look at all the positive terms. And then we can use the arithmetic geometric mean inequality, more precisely a weighted version of this arithmetic geometric mean inequality. And this gives us this larger than or equal sign. And if we use the precondition, then we obtain to the right-hand side exactly the absolute value of the negative term. And therefore, we see that this that the signomial in this situation is non-negative. That's the connection to the arithmetic geometric mean inequality is always behind. And of course, if we have, this is some kind of a non-negativity certificate, we can easily check using the strategy that this signomial is non-negative. And of course, if we sum these exponential sums, it remains non-negative. And now there's a very crucial idea which goes back to Chandrasekaran and Shah, and they have exactly studied the same elementary situation with exactly just one negative term. And they have shown that the non-negativity of this in terms of the coefficients C alpha and D, now for arbitrarily given coefficients, that this the non-negativity of this can be decided in terms of relative entropy programming, which are certain convex optimization problems. In order to see this, let us assume that we, as before, have only positive coefficients, just one negative coefficients. And it's useful to use the following operator notation. So T nu for a certain vector nu is just the linear combination of the vectors alpha given by the coefficients of nu. We will use this short notation several times in the talk. And once we have this, we can exactly characterize the non-negativity of f in the following way. F is non-negative if and only if there exists a nu, such that all the component, say up to the possibly the beta component, are non-negative. Then the sum of the components of nu must be 0, which can be written in terms of the scalar product. And then also we have that this operator must be the 0 vector. And additionally, some relative entropy conditions. So D is the relative entropy function, which is defined here. And E is Euler's number. And we have this relative entropy condition, that this relative entropy condition must be at most D. And the notation U, Z minus beta, and C Z minus beta correspond to the corresponding vectors up to the component beta. Okay, and this is a convex condition. This is a nice description. And you can always think about this nu as some kind of a dual variable. And actually, in order to prove this lemma, usually one can use some kind of some duality argument, and this is how the relative entropy function comes into the game. Relative entropy function is a convex function if we consider it in both the parameters. And this is also called a jointly convex function. And the relative entropy cone is available in practice. There are software tools which you can actually compute in this with this relative entropy cone. It's a non-symmetric cone, so therefore it just has been really investigated, say, in the last 10 years or so. And whereas the symmetric cones, like the positive semi-definite cone and so on, they have been investigated now for meanwhile 30 years. But one can actually compute with this cone. This is important. Okay, now based on this kind of elementary idea, we have a class of signomials for which we can easily certify the non-negativity. And if we fix a negative term and look at all these signomials arising in this way, we call this the H cone, H for arithmetic-geometric exponentials. And they are by construction all non-negative, these signomials. And then we can also vary over the negative term, pick all the possible negative terms and add all these H cone, take the Minkowski sum of them. And this gives the so-called Sage cone for sums of arithmetic geometric exponentials. And by constructions, all these signomials in this cone are non-negative, and membership in this cone can be formulated as a convex program, namely as a relative entropy program. This gives some kind of nice non-negativity certificates, and therefore, by the method that I have introduced in one of the very first slides, we can use it for optimization. This is the setup I'm starting with. And there have been, in the last years, very exciting developments in this business, and this is also the one where our work starts from. I need to introduce some more concept. And whenever you want to study the geometry of the cone, it's very useful to work with generators. So the cone can also be generated in terms of generators, and these are coming from so-called circuits, and they have a very nice combinatorial structure, very nice combinatorial interpretation. And I would like to explain this to you as follows. So assume we have a certain signomial with a certain negative term beta as before. And then it's possible that we can write this signomial as a sum of two simpler signomials, also with a negative term beta. And therefore, we come to certain generators. And the question is, when can we do this? And for this, it's very useful to look at these dual variables nu that we have seen in the relative entropy formulation. And namely, if this, so if we are in this H cone, there is a corresponding nu by the lemma that was giving the relative entropy condition. And if nu is a convex combination of other non-proportional nu I, which are satisfying all the linear conditions from the relative entropy condition, then F splits. It has a non-trivial decomposition. So therefore, this signomial can be written in terms of simpler signomials. And if we do not have this decomposition condition satisfied, this does not work. And if we do this, we eventually arrive at so-called simplicial circuits. Namely, we have we can basically look at these cones, which are generated by these dual variables nu. And we just have to look at these edge generators of the polyhedral cone, which are described by the polyhedral conditions in the relative entropy conditions on this dual variable nu. So that's a polyhedral cone, and we just have to look at the generators. So therefore, this extracts the polyhedral structure in this nonlinear Sage cone. And whenever we have an irreducible element, then the corresponding supports are just simplicial circuits of the affine matroid on tau on T. This would be the support situation for an irreducible situation. So we have one negative term in the interior of the positive support, and it must be in the interior, because other than that, if it would be outside, then the corresponding signomial cannot be non-negative. So, and these coefficients to describe the convex combination in terms of the barycentric coordinates, they are always corresponding to this vector, which is the vector nu in our dual decomposition, in our dual statement. So always when we think of the vector nu, we can, in some sense, think about the barycentric coordinates, and then one of these components related to the negative terms is just -1. Okay, so these are the circuit decompositions. And once we have that, or why are they useful, they can be described, then they can be used to describe a nice decomposition of the cone. And therefore, whenever it comes to the geometry of the cone, this decomposition is very important. So whenever we look at these simplicial circuits, I denote by capital lambda of t the set of normalized simplicial circuits, normalized in the sense that the negative coordinate is normalized to be -1. And every of these simplicial circuits is a witness for a certain subcone of non-negative signomials. And these are called the lambda witnessed H cones if lambda is denoting a normalized circuit. So the exact definition is not relevant so much. What is important is once we have that, the sage cone can be decomposed into the Minkowski sum of all these circuit witnessed H cones. And then of course we can also add terms which are by construction non-negative, namely just non-negative coefficients times a single exponential function. This is always non-negative. We can of course add them to our Minkowski sum. Okay, and this means that we can describe also the cone in terms of generators, in terms of these lambda witness cones. And this was in the story of these cones were a very interesting phenomenon, because before people realized this coincidence, there were kind of various groups working on these cones. The one was working with the sage cones, the other with the circuit generated cones. It was not so clear that that was the same. And actually, this coincidence was proven by Wang in 2018 and by Murray, Chandrasekaran, and Wierman. What is interesting, and I come back to this, is that this decomposition is in general not irredundant. So one might just get rid of certain of these terms, and we come back to this. This is a result of Lukas Katten, Helen Naumann, and myself. Okay, in the last years, there were a lot of developments in this area. People have, in particular, also looked at constrained versions. So far, we were just looking at the unconstrained versions. And in the early days, people were trying to look at mixes with, say, rather costly Positivstellensätze. Then, and this will be very important for the second part of the talk, there was a very exciting approach, I think, by Murray, Chandrasekaran, and Wierman. I'll come to this in a second. And then there are also more recent developments building upon this conditional sage approach, which then take into account additional also non-convex constraint sets. Okay, in this conditional sage approach,
sorry, one question before
sure.
you proceed. So is there any just like the putting our positive dots for polynomial optimization, is there any complexity bounds for the representation?
There's no Putinar type Positivstellensatz. What is done in these last papers is they develop some Positivstellensätze more in the sense there are certain results on Dickinson and Poff type Positivstellensätze, and they are building upon this class of which still contains certain multipliers in the Positivstellensatz. There are also negative results known that there is does not exist a strict analog of Putinar in this context. Right.
But even for the existing methods, do we have like any complexity bounds on the size of the representation or the analog of the results for?
One can use these type of complexity bounds on these Dickinson and Poff Positivstellensätze to come up with complexity bounds in that setting. But of course, the complexity bounds are rather bad, like often. Okay, let me go on. So now we come to the, therefore, this is a very nice approach for convex constraint sets. Here we work with a convex constraint set, which is called X. And I assume that I have access to the support function of S. So for instance, if the support function, which is defined in this way, as the supremum of y transpose X for all X and X, is a well-known classical convex geometric functional. And if we are for instance, in a polyhedral situation that X is a convex polyhedron, then the support function is nothing else but to determine the support function is a linear program. It's a convex function. If X is polyhedral, then the support function is linear on every normal cone of X. And now we can extend the Sage result for convex sets in a very smooth way. And this is even smoother than all the type of position sets. And there is no strict analogon in the SOS world. And now what we want to do is to check membership for non-negativity on the set X. This is what we want to have. And if X is convex, then we can just modify our convex condition and basically add additively to our relative entropy condition the support function. The support function is also convex, so therefore this remains a convex optimization problem. And if, for instance, our support function is nice, say, for instance, in terms of the polyhedron, we just add here some kind of linear condition in some sense. So it's still like a classical relative entropy program that we still that we have to solve. Okay, we can write this a little bit differently. I will use this notation n beta. N beta, just think again in terms of these dual variables n in terms of this dual variable u. We have all the components to be non-negative. Up to the component beta, we want to have that the sum is equal to 1, and this is the corresponding notation for n beta. Stands for negative beta. Only the component beta can be negative, and this allows to write the relative entropy condition just a little bit simpler by putting all the linear conditions into this into this n beta. Then it looks very, very shortly. Okay. Based on this construction, I mean, the same business works. We can look at the conditional H cone, all these non-negative function on X, which have this certificate, and we can sum over all this. This is called the conditional Sage cone or the X Sage cone. Membership can be formulated as a convex program, and for polyhedral X, this is particularly nice. It can actually be computed. Okay, and now the new work starts, our work starts. And the question was, we had this, when we started our work, was the following. In the unconstrained situation, I told you about this circuit concept, which is very important to study the cone. In the conditional, then there was the conditional situation, which is a very smooth approach towards handling convex constraints. And the question was, is there also some analog, some generalization of the circuit concept in the conditional situation? And the essential answer is yes, if one does it in the right way, but certain interesting things also from the combinatorial perspective happen there. What do we want to achieve? We want to decompose, as before, functions into simpler functions, in particular, so that we also obtain some nice decompositions of the conditional Sage cone, say in terms of a Minkowski decomposition. And I come back to this. So finally, the goal would be to describe the cone, say, for instance, the extreme rays of the cone, and then I will also come back to this irredundant decomposition, both in the unconstrained and the conditional situation. Okay. Now the main new definition comes. What is the analogon of a sublinear of a circuit? This is called a sublinear circuit of T, or for short, an X circuit. And we call a non-zero vector nu star, which is in this set n beta. So all the components of this vector are non-negative up to the component beta. That's allowed to be negative. And then we have that all the components sum to 0. And the first condition is that we must have this support function of this operator, this minus the operator t times nu star. This is, to remind you, this is the operator which describes a convex combination with coefficients nu star. This must have a finite value. This is quite clear also from the formulation that we had on the previous slide, where we saw the relative entropy condition, where we have this support function in the formulation, and therefore this is clear that this must be a necessary condition to have a finite value, otherwise this would not work. And the main kind of irreducible condition is the following one, that if we have a mapping from nu to the support function of minus nu, if this is linear on a two-dimensional cone in the set n beta, then nu star must not be in the relative interior of that cone. So this is something like an irreducibility condition. And recall also that this support function is sublinear. And in some sense, we're interested in studying the situations where the support function is not linear. Again, we can also see this from a point of view of polyhedral geometry. In particular, if the set X is polyhedral, then we can think of these sublinear circuits as the extreme arrays of certain polyhedral cones. And in these polyhedral cones, now we also have to take these support functions into account, which comes into the situation as an additional component. So we consider some lifted versions of cones. Okay, it's a little bit a technical condition. What is important is the following. If we are in the unconstrained situation, then the definition specializes to the definition of circuits that we have seen earlier, to the one which is known from combinatorics, from the matroidal situation of circuits. And in the other situation, the situation can be a little bit more unexpected from the combinatorial point of view, because the negative term does not always have to be inside the positive terms. Therefore, the combinatorics changes to argue that we have chosen the right definition of the right generalization of the circuit concept. You should look at the decomposition lemma that we have seen before. And we can generalize the situation that was the motivation to come up with that definition of the sublinear circuits. Namely, if we have this dual variable in this relative entropy formulation, if we can write this as a convex combination of other non-proportional vectors in n beta, and if this map that we have seen is linear on the convex hull, then F decomposes non-trivial. So basically, by our definition, we capture when a certain signomial splits into simpler one and when it doesn't. Then there are also a lot of other nice properties. So if we have an X circuit, the corresponding positive support is affine-linearly independent, is an affine-linearly independent set. For polyhedral X, the number of X circuits is finite, which we would like to have from the combinatorial point of view. In general, for non-polyhedral X, it's not finite, but in the situation of polyhedral X, we are very close to a combinatorial description that we had seen before. Now, what we can do with that is we can build the same setup. We can generalize the setup that we have seen in the unconstrained situation, and we can decompose our conditional Sage cone as a Minkowski sum of these sublinear circuit witnessed cones. So here we take the circuits, the subcones, which are witnessed by these sublinear circuits. Then, of course, we can always add some signomials which are clearly non-negative. And this is the main decomposition, which is then used to prove some geometric results, which I will show you on the next slides. Okay, before we come to the results on the extreme rays, let me talk about another interesting phenomenon, which is related to these irredundant decomposition. I told you before that there's still some kind of irredundancy inside. And this is a very funny and interesting phenomenon. So this would be a signomial coming from a circuit, the example which is here on this slide. And the funny thing is that if this is a ground support, you cannot decompose it at all. But if you add a certain support point, say if you allow to use also a monomial e to the y, have an additional ground support point, then it's possible to decompose the signomial, but with terms which have different negative coordinates. So this has the original negative coordinate, the first signomial, and the second one now uses this new term as a negative term. And this is both of these functions are non-negative. Both of them have this x-sage property, and this is a decomposition of our original signomial. This is a very interesting, unexpected property. And this leads to the strengthening of the concept to the notion of a reduced circuit, a reduced sublinear circuit. And this can be combinatorially described in a very nice way in the unconstrained situation, namely whenever we add, say, a support point in the convex hull of all the existing point, then we can further split the signomial coming from the circuit. Otherwise, this does not work. And using this concept, we can now write the decomposition of the sage cone as an irredundant decomposition in terms of these reduced circuits. This is also related to some work of Jens Forsgaard and Timo de Wolf, who studied the algebraic boundary of this sage cone. And once we have that, it's now possible to describe very nicely geometric situation of this X sage cone and of the sage cone. Say in the unconstrained situation, we can exactly characterize the extreme ray of this convex cone. This would be an exact description of the extreme ray of this non-polyhedral cone. And we can also carry over this and generalize this concept of sublinear of reduced circuits to the case of this constrained version. I will not go into detail here, but it also allows then to describe the cone, the conditional sage cone, in terms of an irredundant Minkowski decomposition. Let me give a brief outlook. There's more work on this. In particular, there's also a connection to second order cone programming to semi-definite programming. Actually, also David Papp, who was here in this session, has also worked on these kind of semi-definite description of these sage cones. Then one can also exploit symmetry, for instance, of these sage representation. They allow sometimes a drastic reduction of the computational efforts. It's also possible to combine polynomials on the full space with polynomials on this non-negative ortho, which is relevant here. There are, of course, many open questions. For example, understanding the combinatorial structure of these sublinear circuits, further understanding this conditional sage cone, and then, of course, this is a very, I think, important open question. It's one additional tool of handling with attacking polynomials, of finding lower bounds for polynomials, and so on, and to understand better the connection and the hybrid methods, combining, say, sums of squares methods with this approach, which is based on the arithmetic-geometric mean inequality. I think I'm going to stop here. Thank you very much for the attention.
Thank you. Thank you very much for this fantastic talk. Any question for Thorsten? Maybe I can break the ice. Sorry, can you tell us a little bit about the algebraic boundary of this? Well, the boundary of the sage cone. Do we have any efficient method to compute the boundary points or to do some computation on the boundary of this cone? Is it like as nice as the?
Yeah, I mean, it's a general question. There are several answers. Let me give them. Okay, so you ask about the boundary.
Yes.
So what I mentioned on the previous slide is basically a very precise description of the boundary, that we give all the extreme rays. So all the edge generators. Of course, there might also be some polyhedral pieces in this in this boundary parts. But this is, I mean, if you have the extreme rays, this is a very precise description of the boundary. In some sense, what I mentioned, what Jens Forsgaard and Timo de Wolf did, is they looked at the algebraic boundary in some sense, that you can think about the boundary as an algebraic surface. Of course, so it's a full dimensional cone, and then you want to you ask about say equations describing the hypersurfaces which form a certain part of this algebra of this boundary, and they have done some nice work where they actually describe these equations, the polynomials describing pieces, so parts of this boundary. They have a very algebraic viewpoint, whereas our viewpoint here is a very convex geometric viewpoint. But both of them yield very precise description of these, of course, of the boundary.
All right.
From different perspectives.
Right. Very good. All right. Any other question?
So if I can ask a naive question, so are there numerical solvers for sage cones? Are there techniques that are good at?
Yes. So I mentioned this in 1 second during the talk, so many thanks for the question. So yeah, you can actually work with that. So the say, for example, so the exponential cone is implemented in MOSEC, which is a commercial solver. It's a convex optimization tool. And so one can do formulations with these relative entropy cone, and therefore this also allows to work with the sage cone, because this is a very straightforward formulation working with the relative entropy cone. We have actually seen the very concrete description, and this can be done. And also, say in particular, say in our work on symmetries, we have actually also done computation. Actually, there's even more. There are also some freely available tools which can work with the relative entropy cone. And actually, Riley-Murray has also written some package on top of existing solvers, which is even more convenient to work with this sage cone, where you, I mean, do not have to give the formulation that we have seen, but really can work with the signomials, and then basically wraps then writes down the corresponding convex optimization programs and feeds the solver. So it's just some kind of a interface towards relative entropy solvers. But of course, this is a very convenient tool, and this also exists. This has been done recently by Riley-Murray, something like around a year ago. And so therefore you can actually work with these things, and these things are fast from the point of view that they are convex optimization problems. These cones are non-symmetric cones, and this means the interior point methods underlying them are a little bit more complicated than the interior point methods, say for symmetric cones, for example, semi-definite programming. But it's efficient, and it works in practice.
Okay, thank you.
All right. Any other question? All right. If there's no question, let me thank Thorsten for accepting our invitation and giving a talk in our seminar. And thank you very much for coming to our session and staying with us throughout the semester. I hope to see you again in the spring. Thank you very much, and have a pleasant day.
Okay, thank you, and bye.
Thank you.
Have a good day. Bye.